Okay, so now let's continue. Before we do the transfer function, let's talk about impedance again. By the way, we can start with the differential equation, and we can arrive at transfer function from the differential equation. But we can also go from differential equation to using impedance concepts, and then go to the transfer function. Now in ENP 231, we took this route, right? And that's what I'm going to follow right now. I may come back and connect the other direct path, but let's just follow what we did from ENP 231. So first we recognize that for linear for linear elements, all right, we have e to the st. Okay, for linear elements, having an e to the st excitation, the response will also be e to the st. All right. So 1, you have a linear element. 2, we're going to excite it with some e to the st excitation. And 3, given those two facts, the response will always be e to the st. So let's take a look at this. If we have a resistor, well, I'll skip that. Let's just look at the capacitor to make the point here. If we have IC and we have voltage VC, if we assume VC is equal to some voltage V naught e to the st, we're going to excite it with that, then IC is equal to C dV CDT. Right, but now we can actually plug this in since we know the form. And when we take the derivative of VO e to the st, we get S out. And then we get VO e to the st again. So we can rewrite this as S C VC of t. So therefore, we can express VC of t with respect to IC of t. We could take that ratio. And when we do that, we get a constant which is equal to 1 over SC. S comes from the excitation function. So if we excite the capacitor with a voltage of VO e to the minus 2t, then S is going to be minus 2, etc. So we define for e to the st excitation, we define the ratio of V to I of an element as that element's impedance. And we use Z, and oftentimes we'll say Z of S. So we'll have Z of S is equal to VC of T, and I'm going to actually write it as a function of S as well as T, just to be explicit, where excitation, and I don't specify which it is because it could be exciting it with voltage or it could be exciting it with current. Either way, but where the excitation is e to the st in nature. Okay, so that's impedance. So we found that for the capacitor, we had ZC is equal to 1 over SC. For the inductor, it was ZL is equal to S times L. And of course, for the resistor, it's ZR is equal to R. It is not a function of the complex frequency S. And we found that if you write an impedance expression for a network, it is a different way of arriving at the same characteristic equation. So as an example, you say, let me just write that, the impedance expression for a network leads to, or is equivalent to the characteristic equation. So for example, we have our network here, which is C and R, and here's our voltage source. If I go in and I look at what is the impedance I see looking in there, I would see R plus the impedance, or ZR plus ZC, which is equal to R plus 1 over SC. Okay, and it turns out that If there is, and I can write this voltage here is, I'll just call it V, and this current here is I. Now, because the impedance is the ratio of a voltage and current associated with the terminal pair, we would say Zs is equal to I, or V, over I. Now, when we were looking for the homogeneous response, we turned off our external source, right? We set Vg to 0. So the question, and yet we expected there to be some current flowing, even though we had 0 volts. So if we say, all right, we're going to turn off the voltage source Vg, that means that this is equal to 0 over I. And the question is, could I have I that is non-zero when I is equal to Vg over Zs, but is essentially 0 over Zs? Could I be non-zero? Can it be non-zero? Well, only if the impedance is equal to 0 as well. And if you get a 0 over 0, then you could have something that is non-zero. So we go back to our impedance expression, which was R plus 1 over Sc, and we set it equal to 0. I can multiply through by Sc, which would give me RCS plus 1 is equal to 0, which, according to our convention of setting Rc equal to a variable tau, we have tau S plus 1 is equal to 0. This is the characteristic equation. And so we found that without ever having to write a differential equation, we can arrive at the characteristic equation, which will allow us to do the same thing as we did before. In other words, write the natural or homogeneous response straight from the impedance expressions and avoiding the differential equations. Now, better yet, let's combine impedance with the notion of a transfer function. All right, so now we're going to return back to our original example here and pose the question again. We have a voltage Vg and we have a capacitor voltage Vs, and we want to know what is the capacitor voltage in terms of Vg. Well, if we replace these R and Cs with impedances, we would have, I'm going to just draw boxes for the moment to be general, indicating that these could be any element. I have an impedance ZR, and I have an impedance, or I'll say Z2, and an impedance Z1. And I have VC and VG. Now, if we use the old voltage divider formula, we notice that VC is simply a voltage divided version of VG. It's Z1 over Z1 plus Z2 times VG. So if I want to find VC as a function of VG, it looks like this might be useful. So let's fill this out. Z1 is equal to 1 over Sc, because it's the capacitor impedance. Z2 is equal to R. I'm going to multiply through by Sc to get 1 over 1 plus SRC VG, and I'm going to write it one more time. VC is equal to 1 over 1 plus tau S times VG. And here again we get this 1 plus tau S. This is the characteristic equation in the denominator of this, what is known as the transfer function. So we would write VC is equal to the transfer function times VG, and I could describe the system in a block diagram as having this H of S block, and I put VG in and I get VC out. And I can use the transfer function to find the natural response and the forced response as well. So first we have to recognize that the denominator, d of s, right? So if I write h of s is equal to ns, some numerator, over d of s, the denominator d of s provides info on, or provides the natural or homogeneous response. And the reason is that the denominator always contains the characteristic equation. In fact, if I simply multiplied through by 1 plus tau s on the top and bottom, I would arrive at 1 plus tau s Vc is equal to Vg. Now, does that not look very much like the differential equation? I could return this to the differential equation by replacing the s with the derivative. Right? This is the differential equation. And notice that the denominator in my transfer function is associated with the coefficients that are operating on my unknown or my dependent variable Vc. Right? They describe, the homogeneous differential equation. So that's why the homogeneous response or natural response is held or contained within the denominator of the transfer function. And as we saw, the transfer function is synthesized or derived by simply applying regular nodal mesh circuit analysis techniques, but instead of using resistors as elements, we use impedance. So we found the natural response from the denominator. We can find the forced response due to sinusoidal excitation. Okay, in other words, something that's sinusoidal. Okay, by evaluating the magnitude and phase of h of s. All right, and we'll show an example of that. So I'm not going to repeat finding the natural response using the denominator, because in this example we've already done that. We know that it's 1 plus tau s, so we can find the zero of that, which, if you recall, the zero in the denominator is called a pole because it makes the transfer function blow up. So its magnitude pokes up like a pole. Instead, I want to focus on sinusoidal steady state. Sinusoidal steady state using the transfer function. Okay. So here we have some system h of s, and we are going to excite it with an input that's of the form sine omega t. What's going to come out as a response, assuming the system is linear, which it is, linear and constant coefficient, so we call it linear time invariant, the response is going to be the same sine omega t. That won't change. However, it will be scaled according to the magnitude of h of j omega. So the magnitude of the transfer function evaluated at the value of s that we're exciting the system. And you might say, well, wait a minute, where did the j omega come from? Remember that sine, or let me call it, okay, so, all right, so sine, we'll leave it at sine. Sine omega t is e to the j omega t minus e to the minus j omega t, the whole thing divided by 2j. Remember, just like we had cosine omega t is equal to e to the j omega t plus e to the minus j omega t over 2. And this all comes from Euler's formula, right, which says that e to the j x is equal to, or ix is equal to cosine x plus j sine x. Okay. Now, in this case, we are we're exciting it with more than just e to the j omega t. We're exciting it with e to the j omega t minus and e to the minus j omega t. But they're both the same. They have different signs, but same magnitude frequency. And by virtue of superposition, we can, we've shown, I'm not going to go through it again here, but the response will basically be a sine omega t, but where the magnitude is modified by the magnitude of the transfer function evaluated at that j omega, and where the phase is going to be changed. So instead of being pure sine omega t, it'll be sine omega plus some angle, and that angle will be the angle of the transfer function evaluated again at that excitation frequency. Okay, so let's do an example. So let's suppose that we have, let's see, this R and the C. I'm going to say the R is, let's say 2 ohms, and the C is, I don't know, 6 millifarad. Okay, and we're going to excite this. I don't know why I chose that. Let me pick something easy here. We'll say 5 millifarads, right? So that tau is equal to RC, which is going to be 10 milliseconds, right? Which is equal to 10 to the minus 2. Okay, and we're going to excite this at, let's say, 5 times sine of 100 t. All right, and the question is, what is the voltage Vc of t? Not transient, not like in the natural response, how it starts up, but what does it look like in steady state after things have settled out? So the particular response. Well, Vc is going to be equal to 5, because that was the amplitude that we're driving the system with, times the magnitude of the transfer function evaluated at j times 100, because this here is omega, times sine of 100t plus the angle of h evaluated at j 100. So all we have to do is find the magnitude and the angle of h. So what is h? Remember, h of s we found on the previous page is 1 over 1 plus tau s. Tau in this case is 10 to the minus 2, so it will be 1 over 1 plus s. I'm going to write it as this s over 100. Okay? So h of j 100 is equal to 1 over 1 plus j 100 over 100, which is 1 over 1 plus j. So we need to find the magnitude and the angle of that. The magnitude of h, let's write this, the magnitude of h evaluated at j omega is equal to the magnitude of the numerator evaluated at j omega divided by the magnitude of the denominator evaluated at j omega. So we can write this as h of j 100 is equal to the magnitude of 1 over the magnitude of 1 plus j, which is equal to 1 over, this is square root of the real part squared plus the imaginary part squared. Therefore, the magnitude of the transfer function at 100 radians per second is equal to 1 over root 2. The angle of h of j omega is equal to the angle of the numerator minus the angle of the denominator. So we can write h of j 100 is equal to angle of the numerator 1. And the angle of 1, if you look at it on the complex plane, so we have real and imaginary, and here's 1 out here. So this thing is pointing like this. It has an angle of 0, right? 0 degrees. Minus the angle of 1 plus j. Now that's sitting here at 1 and 1, right? And so the angle here is 45 degrees. It is equal to 0 minus the arctan of the imaginary part. It'd be the imaginary over the real part, which is equal to, in this case, 1 over 1. So we have this equal to minus 45 degrees. And so now we can write the steady state response is Vc equal to 5 over the square root of 2 sine of 100t minus 400 degrees, not 45 degrees, which is equivalently, what is that, pi over 4, right? Pi over 4. So what does that mean? If you have, if I'm putting this sinusoid, this excitation in, sorry, not a very nice sine wave. If this is Vg of t, then Vc of t is 1 over root of 2 is 0.707, and it's delayed by pi over 4, so it would be like this, and it would be, let's see if I can do this, something like, okay, so this would be Vc. So this is time, so it's delayed, this is delayed by 45 degrees. All right, you say, well, how much time is that? Well, remember, have the 45 degrees, or pi over 4, would be equal to omega times t delay. So the delay would be equal to pi over 4 divided by 100 radians per second. So it's delayed by pi over 400 seconds. That's how much it's delayed by. Or in other words, it's delayed by an eighth of a period. And then the amplitude is reduced to 1 over square root of 2, which is approximately 0.707. So recapping, we use the transfer function to both find the natural response, but then in this case we used it to find the steady state response to a sinusoidal excitation. How did we get there? We started out, let's recap here, kind to wrap this up. We have VI, or effort flow element relationships. Plus conservation laws. Okay, so this would be like the KVL, KCL. Okay, if you were doing mechanics, you'd sum all the forces. It'd be like the D'Alembert's principle. You'd sum all the forces to be zero. So you take these and you arrive at differential equation. Okay, that's one way to do it. You could also take, you could go down to the impedance Z of S representation, and combine that with the conservation laws, and you can arrive at the transfer function H of S. Right? S. And then from the transfer, and let's try to draw this out. You can go to the characteristic equation from here, and you can arrive at the homogeneous response. We can also arrive at the homogeneous response by taking poles of the transfer function, right? Because the poles of the transfer function are just the zeros of the denominator, which are the zeros of the characteristic equation. So we can arrive at the homogeneous response like that. And then we could also arrive at sinusoidally excited steady state response by evaluating the magnitude of H and the angle of H, which is what we just did. Now what we did was we also used the differential equation to find the forced or steady state response to piecewise constant excitation. And you can also use that. You can use the transfer function to achieve that as well. But I won't go into that at this point. So I will stop here. Think about whether I've missed anything. I think what we will do in the next lecture then is to take the transfer function and use it to actually produce frequency response plots that essentially express the magnitude and the angle of the transfer function over a range of frequencies. And so kind of in one shot, one picture, you get this sense of how the system performs as it is excited at different frequencies. And it's a different view of the system characteristics. All right? Just like if you see the natural response of a system, you see that it exponentially decays with a time constant of 3 seconds. That tells you something about the character of the system. We're going to find that if you plot the frequency response, that will also tell you the same information, but it's in a different, presented in a different format. All right, we'll end there.